Hi everybody, this is Mr. Folly, and welcome to podcast 5.3, where we are going to explain how products are based on valence electrons, trends in the periodic table, and chemical properties. So the explanation of why they happen. Explain how balanced reactions show the law of conservation of mass in atoms. Use Coulomb's law to determine solubility rules. Hey, we did that already. And determine if the reaction is endothermic well, it can't be and, or exothermic. Construct an energy diagram and Tony bonds. Let's do it. Oh, don't jump around. What patterns for products can we see? Charges must cancel. So we know that, right? If I have barium plus 2 and I have nitrate minus 1, I need 2 nitrates to cancel the charge and get BaNO3 taken twice. A good Lewis dot structure must form. So we talked about the Lewis dots. We should be able to see that a good Lewis dot structure must form. That means no single electrons and orbitals are full, which is usually 8, right? And we should see a pattern in the periodic table. Aluminum, notice the same. This is a halogen. So Al plus Cl2 gives me Al plus 3, Cl minus 1, AlCl3. Whoops. AlCl3. Also, it's a halogen. Al plus 3, F minus 1, AlF3. Now, this is a halogen. Maybe I can just go smarty pants and do AlBr3.
Hi.
So Al plus O2 is not a halogen. It's in the oxygen group. So it doesn't. But I should be able to predict, what if I had iodine? Oh, I'll get Ali3. If I have oxygen, I have Al plus 3, O minus 2. And that's one way we can help. Will give me Al2O3. So I can identify an unknown based upon the subscripts. Balancing shows the same number of each type of atoms on both sides. This shows atoms are never created or destroyed. So notice here, we're balanced. I have 4. We're balanced, I have 4. So why? Balancing shows that atoms are never created or destroyed. So that means law of conservation of mass. So know that. That's why I balance equations. Coulomb's law helps us determine if ionics are soluble. For products Q's, those are charges, are 4 or more, the ionic bond is stronger than the water's attraction. It is insoluble. Know the rationale behind that. Don't say it's bigger than 4. Say it's bigger than 4, which means that it's more attracted to itself. Hydroxides are exceptions. If the Q's product is 2 or more, it is insoluble. And chlorides are precipitates with silver, lead, and mercury, and guess what? So are bromides. And guess what? So are iodides. And that covers about 95%. Plus 1, minus 1, soluble. So I would call that aqueous. Plus 1, minus 2, aqueous. Plus 2, minus 2, precipitate. Plus 2, oh, again, 2 times 2 equals, I'm just trying out here, 4. 1 times 2 equals 2. 1 times 1 equals 1. So this is precipitate because it's 1. 2 times 1 is 2. Now that is a precipitate because it's a hydroxide, and so on. Heat is also a product or a reactant in a reaction. If heat is a product, it's called exothermic. Heat or kilojoules on the right. So if I have reactants yield products, my heat would be on the right for an exothermic reaction. That's what that means. Delta H is negative, or I could say reactants yield products. Delta H is negative 25. Products have less energy than the reactants. So that means, notice if this is losing heat, if heat is a product, that means the products have less energy than the reactants. That means the products are more stable. It feels hot, and more bonds form than break. What this would look like in terms of an energy diagram would be, and you have to label your reactants and your products. And this guy right here is delta H. Notice how it goes down. This is my energy. This is time. Okay, hope you can draw that reaction. Oh. So focus on the reactant. Endothermic, the prefix endo means in, So heat is on the inside. So heat is a reactant. So I'd have reactants plus heat equals products. Heat or kilojoules is on the left. Or I can say 35 kilojoules plus my reactants yields products. Delta H is positive. Or I can have reactants yield products. Delta H equals positive 123 kilojoules. Products have more energy than reactants. That means the products are a little less stable. And it feels cool because, again, it's absorbing the heat energy. Okay? More bonds break than form, and the picture of it will be like this. Here are my reactants, here are my products. Remember, breaking bonds increases energy, so that right here, this is break, 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 break. Form, form, form. That's it. And this is energy. This is time. Draw an endothermic energy diagram. Boop. I just did that, but I'll draw another one. Ooh. Products, reactants, oops, reactants, break, break, break it down. Whoa, whoa, whoa. Form, form. Keep touch this. Draw an exothermic energy diagram. Show enough. Wow. Reactants, products, break it down, break, 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 break it down, break, 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 break it down. Falling, forming, falling, forming. Easy cheesy. Review, you got that right there, and you got yourself a happy podcast that is all finished. Toodles.